Next, we look at evaluating the effectiveness of the Latin square design. The Latin square is designed to account for, and therefore remove from experimental error, variation from two sources that are not of interest to an experimenter in terms of answering specific research questions, and therefore they are considered to be extraneous, but which are nonetheless acknowledged by the experimenter to be potential sources of significant variation which, if not accounted for, could make the experiment less efficient. When the Latin square design has been used in an experimental situation and after the experimental data have been obtained, an important question to consider is whether the design has, in fact, been effective in removing extraneous variation associated with the two sources used in setting up the design, and if so, to what extent the design has provided more information than would have been provided had at least one of the two sources of extraneous variation not been accounted for. This is important for the purpose of planning future experiments. Now, one way to assess the effectiveness of this two-way blocking aspect of the Latin square design is to consider the F-statistics for rows and for columns. Now, recall that the statistical model for the Latin square design, the means model version of that model, looks like this. Okay. In addition, recall that the assumptions about the row and column random effects include the variance of the row effects, being denoted by sigma squared sub rho, and the variance of the column effects, which is denoted by sigma squared sub gamma. So sigma squared sub rho is the variance of the row effect, and sigma squared sub gamma represents the variance of the column effect. Now, if sigma squared sub rho is equal to 0, then there is no variation due to the row blocking factor, and so it may be unnecessary then to account for that factor in the future. Similarly, if sigma squared sub gamma is equal to 0, then that means that there's no variation due to the column blocking factor, and so it may be unnecessary to account for that factor in the future as well. Hence, it is informative for the purpose of planning future studies to determine whether variation exists from either of these two sources. Now, one way to do this is by testing hypotheses about each of sigma squared sub rho and sigma squared sub gamma. So let's look at this, assessing the row blocking factor. The F statistic for the row effect can be used to assess the effectiveness of the row blocking aspect of the Latin square design. Here is what its F statistic is testing. The null hypothesis is that sigma squared sub rho, the variance of the row blocking factor, is equal to 0. In other words, the null hypothesis is that there is no variation due to the row blocking factor, against the alternative hypothesis that sigma squared sub rho is greater than 0. And so that would indicate that there is variation due to the row blocking factor that does exist. Now, the alternative hypothesis does not say how much variation exists, it just tells us that variation does exist. Now, the F statistic for testing these hypotheses is F sub r, the F statistic for the row blocking factor. That is equal to the ratio of the mean square for rows to the mean squared error. The rejection rule is to reject the null hypothesis if the test statistic F sub r exceeds the upper alpha percentage point of the F distribution with p minus 1 numerator degrees of freedom and denominator degrees of freedom equal to p minus 1 times p minus 2. Now, the significance level that you use here, alpha, does not necessarily have to be the same significance level that you use for testing hypothesis about the treatments. All right, it's whatever significance level would make sense in a particular context. Likewise, the F statistic for the column effect can be used to assess the effectiveness of the column blocking aspect of the Latin square design. This is what its F statistic is testing. And so again, the null hypothesis for this test would be that there is no variation due to the column blocking factor. In other words, that sigma squared sub gamma is equal to 0. The alternative hypothesis is that sigma squared sub gamma is positive, it's greater than 0. That indicates that variation due to the column blocking factor does exist. The test statistic for this test is F sub c, the F statistic for the column blocking factor. And the rejection criteria, again, is to reject the null hypothesis if this F statistic exceeds the upper alpha percentage point of the F distribution with p minus 1 numerator degrees of freedom and denominator degrees of freedom equal to p minus 1 times p minus 2. Now, as was the case with the randomized complete block design, the effectiveness of the Latin square design can also be assessed via its relative efficiency, but the question is, efficient relative to what? Well, it turns out that because the Latin square design essentially has two blocking components, there is more than one design to which its efficiency can be compared. So let's look at quantifying the effectiveness of the row blocking factor. The efficiency of the Latin square relative to the randomized complete block design, where the row factor has been omitted and the column factor is being used as the blocking factor in the randomized complete block design, is given by the following relative efficiency. So I'm going to denote this by capital RE subscript R, so the relative efficiency with respect to the row blocking factor. All right, and so again, what we're doing here is thinking about omitting the row blocking factor, but retaining the column blocking factor. And so if we do that, then we could think about doing that experiment using a randomized complete block design in which the column blocking factor is the blocking factor for that randomized complete block design. And so this is a way of quantifying the extent to which the row blocking factor is effective in removing extraneous variation. And so the relative efficiency for this particular comparison is the mean square for rows plus p minus 1 times the mean square error divided by p times the mean squared error. And again, all of these mean squares are obtained from the analysis for the Latin square design. We can also quantify the effectiveness of the column blocking factor. The efficiency of the Latin square relative to the randomized complete block design, where the column factor in this case has been omitted and the row factor is being used as the blocking factor in the randomized complete block design, is given by this expression. All right, and so I'm denoting this RE sub C, relative efficiency of the column blocking factor. And so the idea here is that instead of using a Latin square design with both of the blocking factors, the rows and columns, suppose we omit the column blocking factor but retain the row blocking factor. With a single blocking factor, we could conceive of performing the experiment using a randomized complete block design. And so that is the comparative model here. Right, so what is the relative efficiency of the Latin square design compared to that particular randomized complete block design where we've omitted the column blocking factor, but we're using the row factor as the blocking factor in that RCB. And so here is the expression. Here's the way we calculate that efficiency. Right, MSC plus P minus 1 times MSE divided by P times the MSE. And again, all of these mean squares are computed or obtained from the ANOVA table for the Latin square analysis. And then finally, what if we were to exclude, what if we wanted to evaluate the effectiveness of including both blocking factors, the row blocking factor and the column blocking factor, together? We want to see, get a sense of how effective they are together. And so one way to do this would be to consider not utilizing either of the row blocking factor or the column blocking factor, excluding or omitting them both. And if we had no blocking factors, then we could conceive of doing the experiment using a completely randomized design. And so if that were the case, what would be the efficiency of the Latin square design compared to that completely randomized design? And so that is what we're looking at here. The efficiency of the Latin square relative to the completely randomized design, where both the row and column factors have been omitted, is given by this expression. So here I am denoting this by RE with an R comma C in the subscript, so that means I'm omitting both of those blocking factors. All right, and the relative efficiency computed this way, which compares the efficiency of the Latin square to the efficiency of the completely randomized design, is MSR plus MSC plus P minus 1 times MSE all over P plus 1 times MSE. And again, all of these mean squares are obtained from the ANOVA table for the Latin square analysis. Now, how do we interpret these values? As before, a given relative efficiency value gives how many times larger the number of replications would have to have been using a particular simpler design in order for that simpler design to provide the same level of efficiency as that provided by the more complicated design, in this case, the Latin square. If a particular relative efficiency is equal to 1, then the particular blocking factor under consideration has not been effective at a simpler design, and the simpler design being used as the comparator could have been used. Now, to the extent that a particular relative efficiency is greater than 1, then a blocking factor under consideration has been effective. So the greater the relative efficiency value, that's an indication that the more effective that the blocking factor has been. So if the relative efficiency is greater than 1, and if it's in particular it's equal to k greater than 1, then what that means is that the simpler design being used as the comparator would have required k times the sample size that was actually used in the Latin square. I see I've got a typo here, let me fix that, but it would used in the Latin square design to have its same level of efficiency. So let's look at an example. This will be example 4.2. And so the question is there variation due to the row and column blocking factors in the data set that we looked at, or in the experimental situation that we looked at back in example 4.1? And so refer back to example 4.1, in which a Latin square design was used to compare 5 treatments. The question that we have now that we have the data, we performed the analysis to construct the analysis of variance and perform the initial hypothesis test over whether there are differences among the population treatment means. For the purposes of future studies, it will be of interest to know, is there significant variation due to rows? Is there sufficient or significant variation due to columns? All right, that would warrant doing these kind of experiments using a Latin square design in the future, or could a simpler design be used? And so again, these two questions: is there variation due to the row blocking factor, that is the shelf from top to bottom in the oven? And also, is there variation due to the column blocking factor, the position in the oven on a shelf from front to back? Okay, so again, here is the ANOVA table from the spreadsheet that I've constructed. And for reference purposes, I'll include this here because we're going to need the mean squares and the F statistics for performing these, for answering these questions. And so the first question we'll look at is there variation due to the row blocking factor. And so what we're going to do first is look qualitatively at whether or not there is variation due to each of the row and column factors. So the null hypothesis being tested here is that sigma squared sub rho is equal to 0. In other words, there's no variation due to the row blocking factor. There's no variation with regard to the shelf, the vertical position in the oven, against the alternative hypothesis that says that there is variation due to the row blocking factor. we'll use a 5% significance level, but again, you could use a 10% significance level or whatever seems to make sense in a particular situation. And so with a 5% significance level, the critical point would be 3.26. Now, the F statistic for the rho blocking factor is 7.1254, and that does exceed 3.26. And so at the 5% significance level, we can conclude that sigma squared sub rho is greater than 0. That is, that variation does exist with respect to the rho factor, the shelf in the oven from top to bottom. And so that would lead us to conclude that in future experiments using this oven, that would be an appropriate blocking factor to use. There is variation with respect to the vertical position in the oven. There's that temperature gradient, and if not accounted for, that would end up in experimental error and diminish the power of hypothesis tests and diminish the precision of estimators. All right, next let's look at the question, is there variation due to the column blocking factor, which is the position front to back on the shelf? And so the null hypothesis here is that sigma squared sub gamma is equal to 0 against the alternative hypothesis that sigma squared sub gamma is greater than 0. So we're assuming that there's no variation due to the position front to back on a shelf, and we're giving the data an opportunity to convince us otherwise. We will again use a 0.05 level of significance. Therefore, the critical point is 3.26. The F statistic for the column blocking factor is 1.3502. That does not exceed 3.26. And so at the 0.05 level of significance, there is insufficient evidence to conclude that sigma squared sub gamma is greater than 0. In fact, there's insufficient evidence at the 0.1 level as well. And in fact, if we look at the p-value for this test, which is 0.308, we see that this is a very non-significant result. So based on this result, if the experimenter were to do future experiments, it would appear here that there's really no need to block on the column blocking factor, in other words, the position front to back in the oven. And so perhaps a simpler design, a randomized complete block design, could be used, excluding the position front to back on the shelf, but including the vertical position, the shelf for the blocking factor in a subsequent type of or a subsequent experiment. Okay, so we've made those qualitative type of conclusions. Now let's see if we can quantify the extent to which these column blocking factors may or may not be effective. And so to do that, we'll look at the following questions. What is the efficiency of the Latin square design relative to the completely randomized design where both the rho factor and the column factor have been omitted? What is the efficiency of the Latin square design relative to the randomized block design where the rho factor has been omitted and the column factor is being used as the blocking factor in the RCB? And finally, what is the efficiency of the Latin square design relative to the randomized block design where the column factor has been omitted and the rho factor is being used as the blocking factor in the RCB? And so the first question, or to answer that first question, we calculate the relative efficiency where we are excluding both the rho blocking factor and the column blocking factor, and therefore comparing the efficiency of the Latin square design to that of a completely randomized design where we have no blocking factors. That relative efficiency is 2.08. And so the interpretation here would be that a completely randomized design would require roughly twice as many observations in order to have the same efficiency as this Latin square design. And so what that tells us is that blocking on either the rho factor, the shelf, or the column factor position, or both, have been effective. Next, we will answer the question, how effective has the row blocking factor or the shelf been? And we'll be actually quantifying that. And so we answer that question by calculating the relative efficiency, which compares the Latin square design to a randomized complete block design, which uses the column blocking factor as the block, and we're completely excluding the row blocking factor. And so that relative efficiency is 2.23. And so the interpretation there is that a randomized complete block design using just the column factor or position front to back on the shelf as a blocking factor would require 2.23 times as many observations as the Latin square design in order to have the same level of efficiency. And so we can see here that blocking on the row factor, in other words the shelf, has indeed been effective. And then finally, we want to evaluate the effectiveness of the column blocking factor, the position on the shelf from front to back. We do this by comparing the efficiency of the Latin square design to a completely randomized design in which the row blocking factor, the shelf, is being used as a blocking factor in a randomized complete block design, and we are omitting or ignoring, we are excluding the column blocking factor. And so the relative efficiency for that comparison is 1.07, which is very, very close to 1. And so the interpretation here is that a randomized complete block design using just the row factor, the shelf, as a blocking factor would require essentially the same number of observations as the Latin square design in order to have the same level of efficiency. And so what we can conclude here, and this corroborates what we found with the hypothesis test, is that blocking on the column factor has not been effective. And so in future studies, again, we just get confirmation of the previous conclusion that we drew, that in future studies and future experiments, it appears that it would not be necessary to block on position on the shelf from front to back, and therefore a simpler experiment could be used, and in particular a randomized complete block design where shelf or the row blocking factor is used as the blocking factor in that randomized complete block design. All right, and then here is just a shot of the spreadsheet that I've got. So before I showed the ANOVA table here, and then down below that I'm calculating the various relative efficiencies. And so, I would encourage you to do these calculations on your own and do them by hand, but also construct a spreadsheet to do the calculations so that you can check the work that you do by hand. All right, so that wraps up this particular section. We will continue on in the next lecture video looking at estimation in the Latin square design.